So today is lecture number 5. We're going to talk about batteries and electric vehicles. And as I'm sure you all know, we have our first homework assignment, homework number 1, which is about ordinary differential equations and linear dynamical systems. This is due tomorrow, just before midnight Eastern. Our TA, Nada, had office hours today and yesterday. Did anybody go to TA's office hours? One person? Okay, great. So let me just try to, again, take the temperature of the room here. So who thought that the homework, first of all, who has finished the homework already? And then who has not started the homework yet?
Just started this morning.
I know you had limited access, so no worries. And everyone else is somewhere in between. So of those who've worked significantly on it, who thinks like it's pretty reasonable, not too difficult? Okay, and then who thinks like actually it's pretty tough? Okay. Yeah, that's all good. And then for, let's see, Grant, if you don't mind me picking on you, you don't have to answer, but between the written questions and the coding questions, was one more challenging than the other?
The code, I guess it was just difficult for me to kind of string between the math and the code.
Yeah.
In a way where I felt confident moving forward versus just plugging in the equations you had on the thing.
Right.
I could do that and successfully finish the code, but didn't really know what was going on.
So the response for folks online is basically the coding was a little bit maybe more challenging than the written stuff, or just the mapping between the code and the math is somewhat challenging. And there's a fair amount going on in the code that I gave you guys. There's like the wrapper scripts, and then there's the functions that they call and how they relate to each other. And then there's like the plotting portions and things like that. So I think what I may try to do, and this may require slowing down the lecture materials somewhat, but I will think about this and whether we have time in the semester. But I think it might be nice to spend 5 or 10 minutes when I assign the homeworks to go through kind of the code and just be like, here's what this chunk of code is doing. It calls this function. Let's look at that function. And just to give you guys a bigger, more clear picture of how the code kind of all works, if that makes sense. I will say, of course, you always have a fallback of office hours, so you can come to my office hours either in person or on Zoom, and then our TA also has office hours, hybrid format. So, and of course, you're welcome to work with friends and things like that too. So, yes.
I think maybe it would be helpful if we do like during the lecture for 10 minutes for the input code.
Yeah.
Like fast, just to understand, because we don't read analytically what's going on there. It's difficult to understand what's.
Yeah. Yeah. So walk through the code a little bit.
Yeah.
Here's the intention. Here's what it does.
Yeah. It's just fast.
Yes.
Yeah, you, I believe, showed us what sort of the finished code should look like.
Yeah.
Maybe even just comparing where you get to in the end versus where like the starting case is. I think just sort of figuring out, like taking stock of what is already there versus what our job is, and sort of more in depth on what exactly we're meant to do.
Yeah. Yeah. Fair. Okay. Thank you for the feedback. I'll take that into consideration. On that note, we have posted homework number 2 on batteries and electric vehicles. So let me just open that. Unless my computer freaks out. So it's 3 problems again. I guess you had a 4th problem on the homework number 1, which was basically entering data into a spreadsheet. So hopefully not too challenging. Here, there's a coding problem again, which will involve basically everything that we'll talk about today, but it will involve essentially replicating some of the simulations that are in today's code. There's also kind of a different flavor of question. These are just short calculations. So they should be, just plugging things into numerical formulas and doing written calculations. So not too difficult, but hopefully trying to give you some intuition for how EVs and batteries and things like this work. And then there's, again, sort of a math section here. Not so different from what we did on one of the problems in homework number 1, but applied specifically to batteries. And then let's see, I just wanted to give you kind of a sense of where we're going. So this is a sheet that I'm mostly, I haven't shared with you guys. I'm mostly using it for my own purposes and trying to coordinate with our TA. But this is kind of a rough schedule subject to change of where we're going in this semester. So you can see here, we are now on lecture number 5. We've been through intro material, we've been through some math background, and now we're starting to work on DERs. And then Thursday, we will talk about buildings, and then another lecture on kind of the thermal dynamics of buildings next week, Tuesday. Then we go into heating and cooling equipment, thermal energy storage, and this includes water heating and things like that. Solar, with a focus on solar photovoltaics. And then lecture 11, not so long from now, I guess about 3 weeks out, will be a summary of kind of this modeling and simulation component of the class. Okay, so then the vision, and I haven't made it yet, italics is things that I have not yet created, so these are very much subject to change, but the vision is basically the week before spring break on that maybe Tuesday or Wednesday to give you a midterm exam. And the vision for that is basically what I want from it is just to kind of encourage you guys to go back, revisit the homeworks that you've already done. If you got lower than perfect grades on some of the homeworks, go in, talk to me, talk to the TA, figure out what it was that you missed, figure out how to correct it, right? Because I'll basically resample chunks of homework problems or something similar to that to use on the midterm. So if you've done all the homeworks, the idea is that this take-home midterm should be quick and fairly easy. But if you have not done the homeworks, or maybe you didn't do them correctly and you didn't catch your mistakes, it may be a challenge. Okay, so I don't know. I think pedagogically, the idea here is just the ideas tend to stick with us longer if we revisit them a couple of times. So if I learn one thing and then I just never use it, never apply it again, the chances that I forget it are reasonably high. But if I have to go back and refresh my memory on it, then hopefully the retention will be a little bit better. And then beyond, so yeah, this is something to flag here. These are deliverables basically that I have in mind for the project. So one point of feedback that I got last semester was that I didn't have really intermediate deliverables and deadlines for the project. So most people left it until like the very end of the semester, and then it was a crazy crunch trying to get everything done. So here I'm trying to keep you guys on track. So you have already done this in homework number 1, where you basically state your interests so that we have a big spreadsheet. We can do like a kind of musical chairs process and match people with similar interests. You also can, of course, form your own teams if you want to, but for people who do not have a team, we'll facilitate that. So we hope that you guys will have all your teams finally formed by mid-February. And then I'd like you to do a little bit of reading of either research literature, project reports, things like that on the topic that your team chooses. And then here we want to have basically some project pitch classes. So I anticipate we'll have kind of around 10 teams. So this would be about 5 pitches per class, and we'll set aside 2 classes for it. But you get up and you just say, here's our topic, here's a little bit about what people have done previously on this topic, here's the kind of unique angle that we want to take, and then a little bit of the plan of what you foresee as the results being. It's impossible to look forward and know exactly what they will be, but kind of what the vision is. And then, so you'll write an outline, kind of a high level outline, and then a more detailed outline of what the paper eventually looks like. Then you will share your slides. We'll have 4 days set aside for in-class presentations. These will be about twice as long as the project pitches, so we have about twice as many days set aside for that. And then I have to turn in final grades on May 8th, so 1 week before that, I'll ask you guys to submit your final presentation. Is there a bug flying around or something? Oh yeah. Rather not get stung by a bee on camera here. Okay, cool. Anyway, so that's just a little bit about where we're going. And then after spring break, so here it's going to be kind of tight for about a month. So you guys will have weekly homeworks, and they'll be about the same length as the one that you guys did for this week. So hopefully you're not spending like 20 hours on the homeworks. Hopefully you're not spending like 1 hour on the homework. Ideally it's somewhere kind of in between. I think it's a ladybug. Some kind of beetle, yeah. Anyway, so that pace will kind of keep up until about the end of February. Then you'll have a week off to kind of go through, study a little bit, and then midterm. And then after the break, we'll probably only have maybe 2 homeworks, so that the pace will slow down really significantly on the homework side. And the idea is that you are ramping up work on the project during that same time. So does that all kind of make sense? Good. Any questions about where we've been or where we're going? Yes.
Can I ask just that at that endpoint there, I see slides are due on like 17th, and then, the talk happens that following Tuesday.
Yeah.
Is already like, is it a hard deadline on the slides or?
So I think, okay, so first of all, like this is a 2-week period. So if you were the first person to go on April 22nd versus the last person to go on May 1st, there's like a lot of time difference, and you can work for 2 more weeks on your project basically, which is not maybe super fair. We're going to try to just assign time slots here randomly, so there's not a lot of like jockeying for position and things like that. But I guess my thought, and this is again not set in stone, but my thought here was that at least getting a preliminary version of the slides from everyone would be kind of like setting a level playing field, if that makes sense. But I think it's probably, it's okay if you send me slides here and then you update them a bit, like don't completely change everything. But, and again, this is kind of just trying to have intermediate deadlines so people stay on track, if that makes sense. Yeah, thank you. Other questions or comments? All right. So. Right, so today we'll be talking about batteries and electric vehicles, which for the purposes of this class, we pretty much just model as batteries that can move around. We'll start by talking about stationary batteries, somewhat simpler than EVs. We'll talk about kind of how we model these things, how they work, and then we'll talk about how to find appropriate parameters to go into the model. So for example, we talked about a battery model, I think last week on Thursday, which had a coefficient tau in it, and that tau is called the time constant. And so we'll talk about how to fix the time constant for a battery as one example. And then we'll talk about EVs, and then some policies basically for how EVs can charge. And then this will relate to your homework problem for next week. Okay, so what is a battery? Well, it's an energy storage system that basically converts between electrical potential energy and chemical potential energy. And so for that reason, we often call them electrochemical energy storage. So electricity goes in, stored as chemical potential energy, and then we eventually get electricity back out. And today, most batteries that we use are called lithium-ion batteries. And there are other types of batteries, lead acid batteries, iron air batteries, lots of other things. And in fact, like there's an enormous amount of research in material science and chemistry departments around inventing new ways to do electrochemical energy storage, new battery materials. But lithium ion has really come to dominate over the last, say, 10 to 15 years, mostly because of energy density and cost of manufacturing. So almost all the batteries in our personal electronics, phones, laptops, etc., are lithium ion. Essentially all electric vehicle batteries, not all, but most of them today are lithium ion. So that includes cars and trucks, but also things like e-bikes and scooters and e-skateboards and so forth. And then most stationary applications also use lithium ion batteries. So energy density is one strong suit of lithium ion, and that's why we use them a lot for mobility applications and portable things. But the cost of lithium ion has come down so much, largely due to economies of scale, due to really, really big manufacturing facilities. So for that reason, we also often use lithium ion batteries for stationary applications where energy density isn't really that important. So these were invented in the 1980s, commercialized around 1991, and I forget the name of the professor, but he's in upstate New York, won the Nobel Prize in, I don't know if it was chemistry or physics, ill-informed today, I guess, but around 2019. So I think it's widely recognized that this technology has really changed the way that a lot of things in the world work. So the main components of a battery, there are 4. There's what's called the anode, which is something whose job it is basically to emit or release electrons and positively charged ions during the discharge, and then the opposite during charging. And the typical material in a battery system for the anode is something like graphite. For the cathode, the material might be something like lithium or metal oxides. And the role of this thing is kind of the inverse of the anode. So it is to absorb the electrons and the ions that are emitted during the discharging process. And again, kind of the opposite when charging. And I'll show a schematic of that in a sec. There's the electrolyte, which is typically a fluid. It allows movement of ions, but not of electrons. So it provides kind of a selective transport medium for only the positively charged ions and not the negative electrons. And this might be a polymer gel, a mix of salts, or other materials. And then there's a separator, something like a membrane, basically, that blocks the flow of electrons, and it prevents physical contact between the anode and the cathode. And so this might be a plastic. So here's what discharging a battery looks like. So here we have the anode on the left-hand side, the cathode on the right-hand side. The idea is that the positively charged, the light blue particles here, are the ions, are emitted by the anode, and they can travel through the electrolyte, which is the kind of gray stripes here, and they can pass through this barrier, the separator. So they move from the anode through the electrolyte and the separator over to the cathode. And so you can imagine then we're sort of losing positive charges over here and building up positive charges over here. So there's a negative charge here, positive charge here that creates a potential difference. And then you have flow of electron through this conductor, a wire, something like that, from the anode over to the cathode. And then as those electrons flow, we use it to provide some work or whatever. So that is the charging process. And sorry, that's the discharging process, getting energy out, chemical energy out and converting to electrical energy. And then the charging process basically is just the opposite of that. So now the cathode emits positively charged ions that travel through the electrolyte and the separator over to the anode, creating this potential difference. And then we have electron flow around the sort of in the opposite direction along the conductor. So yes, question.
So when you're charging a battery, what exactly are you adding into the system? Is it just like positive into the cathode or?
So when we are charging a battery, what are we adding into the system? So I guess we apply a potential difference that causes electrons to flow this way, and it causes positively charged ions to flow that way. So I guess what we're doing is we're moving both positive and negative charges from the cathode to the anode during the charging.
Okay.
It's just kind of useful tips, but this is from the University of Michigan, and it's tips for basically extending the life of a lithium-ion battery. So one rule that I have violated already today is minimize exposure to low temperatures. So actually the other day I came to class early and it was bitter cold outside, like 5 degrees Fahrenheit or something like that. And my computer just wouldn't turn on for a while because the lithium-ion battery was very upset about being so cold. Thankfully it eventually did, and I was able to teach class. But anyway, so you don't want it to get super cold. You also don't want it to get super duper hot. So this is one reason. There are many others, but one reason that laptops typically have cooling systems in them, fans and things like that, to keep the battery cool as it's running. Minimizing the time spent either at 0% or at 100% charge. So intermediate charges tend to be better for battery health for whatever reason. Avoiding fast charging. So if you have an electric vehicle, you can sometimes stop on the roadside at a fast charging station and charge at really high power, 100 kilowatts or more, and get a lot of energy into your battery very quickly. The downside of that is that while it's very convenient while you're driving, it also can, for some types of lithium-ion batteries, it can have health issues for the battery, lead to more frequent degradation. And then avoid discharging more quickly than needed. So again, if an EV, if you drive super duper fast, you've got a lead foot, you're routinely going from 0 to 60 in 2 seconds or whatever an EV can do, then that also may lead to accelerated degradation. And then some other things. So don't bash it, don't dunk it in water, stuff like that. Okay, so back to some math here. We're going to apply some of the basic ideas that we learned last week, kind of in the math module to the battery model here. And actually, this model I already wrote down last week, but just to refresh your memory, a simple model of the battery's energy dynamics here would have a state x, which is the stored chemical potential energy. We take the time derivative of that, and it's proportional to the charge negative of the charge state divided by tau. And this thing is called the time constant, or the self-dissipation time constant. And then we add in the chemical charging power here. So in a case where the chemical charging power is 0, this basically says that the rate of change of the energy stored is negative the energy stored divided by this time constant. So that means we're going to be losing energy if x is positive here. And then the rate at which we lose energy is determined by this time constant here. And then, yeah, for an ideal or a perfect battery with no self-dissipation, that time constant essentially would be infinity. And so dividing by infinity basically zeroes out this term, and then you're just left with the rate of change of the energy stored is equal to the chemical energy that we're putting. And then this thing P can be either positive or negative. If it's negative, it means we're discharging the battery. Positive means we're charging. So I showed this plot last week, but this is basically what the dynamics of a battery look like if you charge at a small positive power for a constant power for a long time. So we begin at an initial state and we end up at a final state here, which is basically the state that balances the energy lost via self-dissipation against the energy that we're putting in by charging. So that's how we get to this kind of final steady state. And then the rate of this approach, this exponential approach, is again determined by the time constant here. So after one time constant, I think we're, what is it, 65-ish% of the way to the final state. After 2, we're 85%. After 3, I think 95, and then 98 after 4, something like that. Okay, another thing to note, and this is new material, we didn't talk about this last week, but there's a relationship between the chemical power that we're charging or discharging at and the electrical power that we're exchanging with the grid. So anytime there's a conversion between different sort of flavors or types of energy, in this case, chemical and electrical, typically there's an efficiency associated with that. So here is a model of the electrical power P that we're exchanging with the grid as a function of the chemical power here. So this basically says if we are charging, then the electrical power going in is going to be the chemical power that actually goes to changing the state of the battery divided by the charging efficiency. So this charging efficiency might be like 95%. It'll be less than 1, which means that dividing by something less than 1 is going to increase something here. So this means that the electric power when we're charging is bigger than the chemical power. Makes sense. So some energy is lost when we go from electrical converting to chemical. And then vice versa, if we are discharging, this discharging efficiency might be 90-95% again. And so the electrical power that we get out of the battery is less than the chemical power that we pull. And then so this piecewise definition here, you can actually write as a function using the max function. So this is a function of 2 variables, and it just gives you the bigger of the 2 variables. So the max of x and y, if x is 2 and y is 3, would just be 3. So you can convince yourself that these 2 expressions are equivalent. And then, yeah, the etas here are just defined as the efficiencies of charging and end of discharge. And so here's what that looks like graphically. So on the x-axis here, we have the chemical power Pchem that we're putting into the battery. So positive if we are charging, negative over here would mean discharging. And then the y-axis, we have the thing I was calling P in the previous slide. So the electrical power that we're pulling from the grid. And so the dashed line here has a slope of 1. So this would mean an ideal or a perfect battery. You would pull the same amount of power from the grid that you end up putting into chemical storage in the battery. But because a battery typically does not have perfect efficiency, we pull more power from the grid than ends up in the battery. And similarly, as we're discharging, we get less power back from the grid than we're extracting from the battery. Yes.
Is there any similarity into like how they might increase efficiency in a battery to like a engine where they might have to like a reheat or some other processes that get done to increase efficiency of the battery? So are there processes that get done to increase the charging or the discharging efficiency of the battery? Not my area of expertise, but I will hazard a guess and say yeah. So I'm guessing a lot of engineering effort has gone into the design of, for example, a lithium-ion battery for automotive applications. And yeah, and a lot of that probably was involved with minimizing the losses, conversion losses. Yeah, and we can maybe find some reading on that if you're interested. Okay, so a homework problem here, fairly straightforward, just applying equations that we found in last week's lectures. But you can show that the discrete time version of this continuous time model that I showed a couple of slides ago is that the new x, where x again represents the stored energy in the battery, the chemical energy. The new x is a coefficient a times the old x, plus 1 minus a times the time constant times the chemical charging power, where this thing a is given by e to the minus delta t, that's the time step, divided by tau. And one way to remember this, if you are trying to remember what the formula for a here is just to note that the arguments of an exponential function, an exponential is called a transcendental function. So a sine or a cosine, something like this is also in that class of functions. But the arguments, the units of whatever goes into the exponential should always be dimensionless. So if you find yourself taking like e to the something that has units of meters or of hours or of kilowatts,
then that should raise a warning flag for you as you're doing your math, because likely you made a mistake somewhere. Okay, so a straightforward homework problem is basically just to derive this using last week's. As we simulate batteries, and eventually we learn to optimize the operation of batteries, it's important to note that batteries have constraints. So typically the energy, there's a limited capacity, right? There's only so much chemicals or whatever that we have within the battery. And so there's only so much energy we can store. And typically we can't go negative in energy. And sometimes there would be a non-zero lower bound here. So you could have an X minimum and an X maximum. But anyway, it's kind of like potential energy for gravitational potential energy. You can always pick what's called the datum of potential energy. You can pick whatever point you want where the zero is. So if I'm thinking about the potential energy of, I don't know, like a block or something that I was holding, I don't know, my phone, I could just, I could say, well, zero is at the floor. And so this thing has, you know, some units of potential energy, but I could also define the zero to be right here. And then this thing would have zero. So the deltas, the changes in energy are always kind of, can be calculated the same way, regardless of where your 0 point is. We also have charging and discharging power limits typically. And these may come from the chemistry of the battery itself, or they may come from like the wiring or the motor that the battery is attached to. And then we can write down the power constraint here. This is written in terms of the electrical capacities, but we can equally well write that in terms of the chemical charging capacities. And you can convince yourself basically that this is true. Okay, so very simple model. And actually, not to give too much away, but many of the DERs that we study in this class, so buildings, the thermal dynamics of buildings, thermal energy storage, water heaters, and various other things can actually be sort of reformulated as energy storage type models. So they look like batteries, slightly different modifications of these equations. But if you understand how batteries work, then it builds a lot of intuition for how these other DERs can work. So we'll move on here to talk about how we fit the parameters or specify the parameters that go into these models, put numbers to the parameters so that we can actually simulate them on a computer. So there are 6 parameters. There's the energy capacity, the chemical energy capacity. There are the charging and the discharging power capacities. And then there's the self-dissipation constant, time constant, tau. And then there are the charging and the discharging efficiencies. So we have 6 things to figure out. And the particular values of these things will change depending on the kind of battery that we're simulating. So a huge, power grid scale battery plant would have very large values of these things. They might be quite different from what we would have, for example, with a home battery in a basement or an electric vehicle battery. Okay, so we'll start with the time constant tau. Okay, so I'm sure you've all had this experience where you charge a tablet and then you don't use it for a few days. It was full charged, and then you pick it up and use it 3 days later, and it's at 90% or something like that charge. So a typical battery, a healthy battery, without any kind of parasitic stuff happening on it, might lose on the order of 1 to 3% of its energy that's stored per day. So if we take the battery equation and we set the chemical charging power equal to 0, so we're neither charging nor discharging, and we set the initial state at some x naught, could be 100%, could be 80%, whatever, then the solution to that battery equation, the continuous time equation, is very simple. It's just exponential decay. So we get e to the minus time divided by tau times the initial state x naught. That is the state at time t. So after 1 day, we can plug in t is equal to 24 hours, and we find that the ratio x divided by x naught is just e to the minus t on tau. We know what t is. And so this gives us a way to basically calculate what the time constant tau is. So here we take tau, basically just rearrange this formula here and solve it for tau. We get a log is the inverse of the exponential that shows up there. And then you can run the numbers and find that a typical value for a time constant might be on the order of 1,000 hours for a healthy lithium-ion battery. I have a tablet at home that loses like 10% energy per day rather than like 1% energy per day. And I don't know why, and it's kind of annoying, but there the time constant would be much shorter, right? So we'd be dividing by log of 0.9 rather than log of 0.98, something like that. By the way, there is a homework problem which is about finding the dissipation time constant of something. Okay, how about the energy and the power capacities? Well, in general, if you're trying to specify or design a battery for a given application, choosing those capacities is sort of a design problem. But there can be constraints on that design problem that come from hardware limitations. For example, how thick the wires are that run from your battery to your house. But for most stationary lithium-ion batteries, if you look at kind of popular models that are out there, typically they have the same or very similar charging and discharging power capacities. So these two are roughly equal. And if you look at the ratio of the energy capacity to the power capacity, so that would be units of kilowatt hours divided by kilowatts. So that's units of hours. Would typically be on the order of 1 to 4, something like that. So that's one way to talk about how big a battery is to specify its power capacity. It's a 5 megawatt battery, and it has 4 hours of storage. That would tell you it has 20 kilowatt hours of storage. So that ratio seems to be fairly consistent across different applications for lithium-ion batteries. And then, yeah, there may be limitations from the wiring in a building. Basically, how fat the wires are determine how much current can safely flow through it before it risks overheating. And then what voltage the system is at. Typically in homes in the US, we would have either a 240 for a large appliance or a 120 volt outlet for smaller appliances. So depending on the voltage and the current, we might get a power limit from basically IV there, the product, which is how much power can flow through. And then I think this is for a Tesla Powerwall, but there are many other home batteries that you can look at where the P and charging and discharging power limits are about 5 kW, and then the energy storage is about 13.5 kilowatt hours. So this is for, again, a Tesla Powerwall. So the ratio here is about 2.7, which is pretty close to the midpoint of this 1 to 4 hour range. Okay, so that's, let's see, we had 6. We went through the time constant, that's 1. Energy and power capacities, 2 power and 1 energy capacity. So now we're at 4. So 2 more parameters to go. And these are the efficiencies, the last 2. So one way to specify the efficiencies is to think about what's called the round trip efficiency of a battery. And so in words, this basically means if you put some energy in, say 1 unit of energy in, and then you take, basically charge the battery to full from 0, and then you discharge it down again, how much energy do you get back out, basically? And it's usually around 90%, something like that for a lithium-ion battery. So let's imagine an ideal battery. Let's not think about self-dissipation. So imagine doing this charge-discharge experiment quickly so that the self-dissipation is not really relevant. And let's imagine the first step here, we go from, and we'll use the discrete time version of the dynamic model here. So at time k, we begin to charge, and we put in a power P in over 1 time step, say 1 hour. So then from the discrete time dynamics, we would get that the next x, so 1 hour later, is equal to whatever the initial x was, plus the time step, delta t, times the charging efficiency, times the power Pn. So this is electric power here. And then suppose that, so we do that for over 1 hour, say, if we're using 1 hour for the delta t here. And then over the next time step, next hour, we basically do the opposite. So we return the battery to its initial energy state. So that gives us this equation at time 2, or k plus 2, we get basically a return to the initial energy. Let's see. Xk plus 2, we can apply the discrete time dynamic equation. So that's just xk plus 1. In this case, we're minus the delta t times the power output. And then we divide by the conversion efficiency because we're dealing with chemical energy here. And then right-hand side of this equation hasn't changed at all. And then we have an expression up here for xk plus 1 in terms of xk and the charging power Pn. So we plug that in for xk plus 1 here, and we get this long equation. And then stuff drops out here. So the x's drop out. So the result that we're going to get here, it turns out, is independent of the initial state of the battery, whether it was at 50% charge or 0 or somewhere in between. And then the delta t's here will also cancel. So we get this equation here that the charging efficiency times the input power equals the output power divided by the discharging efficiency. And then if we want to ask, basically, how much power do we get back out of the battery after we put power P in to the battery, it ends up being the product of these efficiencies times the input power. So this ratio here of power output divided by power input is called the round trip efficiency. So P out will be less than P in. So divide through, we get something less than 1. So this product here will be less than 1. Any questions about this? Yes.
If charging and discharging are the same, you just like square that term and then.
Yeah. So the question is, if the charging and discharging efficiencies are about the same, can we just say it's eta? This is eta squared rather than eta C eta D. And the answer is yes. That's a pretty good way to come up with these. So that is what I'm talking about here. So the round trip efficiency of a typical lithium-ion battery might be around 90%. And again, it's a reasonable assumption, absent other information, it's reasonable to assume that the conversion efficiencies for charging and discharging are similar. And in that case, we can just take the square root of the 0.9, that ends up being about 0.95. So, plausible kind of first cut would be to set the charging and discharging efficiencies to about 95%. All right, so to summarize here, time constant might be order of 1,000 hours. The charging and discharging efficiencies around 95%. And then for coming up with the energy and the power capacities for the battery, if we're thinking of it kind of in a design sense, we can pick the energy capacity for the application. So I don't know, for example, if you say, I want to be able to drive in an electric vehicle 200 miles on one charge. And then you have a sense for how efficient the driving of the vehicle is, then that tells you basically how much energy you need to store. And then typically the power charging and discharging capacities would be roughly equal, and you can initialize them kind of not super precisely, but as sort of a first cut plausible value by taking the energy capacity and dividing by somewhere between 1 and 4. Conversely, if we're thinking about maybe a stationary battery for use inside of a building, we can say, well, look at the building's wiring and say, is it 240 volt outlet or 120? And, how thick are the wires? Can they accommodate 10 amps or 20 amps or something like that? And then based on that information from the building, we set the product IV equal to the charging and the discharging capacities. And then again, we use the same relationship, kind of this factor of 1 to 4 difference between the energy and the power capacities. Questions? Yes?
So if we were told, without any other influence, just after in the room, that our battery would fully drain itself in X days, then would we set the X days to 4 tau, or would we try and which assumption would you suggest making there?
Yeah. So the question, and I'm not going to fully answer this because it's basically a homework problem, but is suppose that you observe that you have some battery and after 4 days, it loses basically all of its charge. How do we back out what the time constant is in terms of that 4 days? And the question was, well, can we just say, assume 5 time constants? After five time constants, you're at 99% of the way to the final state. So that would be a reasonable approach. You'd probably get pretty close if you use that. But the way that I'll ask you to do it in homework is to think about the equation that I showed a few slides back. I guess I'll be nice and even just show you what slide to look at here. So we get this equation basically relating the initial state, the initial state x naught and the eventual state after a time t. So here for your problem, you could say t is equal to 4 days. Let's use units of hours, so call it whatever that is, 96 hours. And then, the initial state, say, is 1 or 100%, and then set x of t equal to 0. Well, I guess this doesn't really work if the final state is equal to 0, but set it to something quite small. and then basically you can use this equation down here to solve. But yeah, I think like looking back at this thing, after 5 time constants, you're very, very near the final state. So that would be another approach, would just be to take the final state and divide by about 5. And so as a rule of thumb or a check, you could do both approaches and try to convince yourself that they are similar. Yeah. Okay, so that's stationary batteries. Now we'll talk about electric vehicles, which are a pretty straightforward extension of the stationary battery material. But any questions about stuff we've talked about so far before we kind of shift gears. All right. So yeah, I've said this a couple of times now, but basically EVs we assume have basically the same dynamics as stationary batteries. So this is the same discrete time dynamical equation that we wrote down, and it comes from the same kind of continuous time ODE model of the battery that we put up on one of the early slides. But now the chemical charging power or discharging power, we have to think about what happens in two cases. One, when we're charging. In that case, is basically the same as what we've already talked about for a stationary battery. And then the other is when we're driving. So there, the rate of discharge of the battery is related to how far and how fast we're driving, how heavy the vehicle is, and things like that. So suppose a vehicle drives a distance d at time k, so between times tk and tk plus 1. And we assume that we're using a constant time step of delta t. In this case, we get that the chemical charging power can be expressed as the negative. So it's going to be less than 0 because we're taking energy out of the battery in order to drive. Alpha, and here alpha is called the energy intensity of driving, and it would be in units of kilowatt hours per kilometer. So this is kind of the inverse of what we would have for combustion vehicles of a miles per gallon type rating. So we want miles per gallon to be high. We want energy intensity to be low. You could just as easily use a 1/alpha and then have kind of a direct relationship between miles per gallon and kilometers per kilowatt hour. But anyway, I've chosen to write it in this way for whatever reason. So we take the energy intensity of driving in units of kilowatt hours per kilometer, multiplied by the number of kilometers we drive. That will give us kilowatt hours on the numerator here, and then divide by delta t. And the sort of implicit assumption here is that I guess we're driving at kind of a constant speed, so that the charging power is sort of constant over the time step. Anyway, we take kilowatt hours divided by delta t. The duration of the time step could be 5 minutes, could be 1 minute, could be an hour, and we get the chemical charging power for the time step. So what influences this thing alpha, which we call the energy intensity? I mean, again, if you have a car or are used to thinking about cars, you will have thought about miles per gallon and all the things that influence that. And so it's basically the same for batteries, but with a few additional considerations. So how fast we are driving is one important consideration. So wind resistance of a vehicle, you're a fluids person, but I think it goes kind of like the cube of the velocity. So as you drive faster and faster, the force with which the wind pushes against the car goes up kind of cubic. So when you're driving slow, not much force resisting you, but as you get faster, it goes up really quickly. Also, the weight of the vehicle. So if we think of uneven terrain, we're going up hills and then coming back down them. Electric vehicles typically have what's called regenerative braking. So you spend energy going up a hill, but then as you come back down, you recover some of that if you're riding the brakes as you come down the hill. Anyway, the weight of the vehicle, how hard you have to push basically to lift the vehicle up to the top of a hill obviously matters. The shape of the vehicle matters, so aerodynamics. And then the efficiency of the drivetrain, right? So how efficiently do we convert that stored chemical potential energy into kinetic energy, the motion of the vehicle? So this has to do with motor efficiency and things like that. And then, related to this weight issue is the terrain issue. So if you're going up and down hills repeatedly, you can imagine you're going to use more energy than sort of driving on a flat landscape. And the weather as well influences, and quite significantly influences the efficiency or the energy intensity of driving an electric vehicle. And this is for two reasons. One is that when it's really cold outside, for example, last week here in Indiana, you would be running a heating system to keep the cabin of the vehicle warm. And so that's going to use additional energy that's stored in the battery. For a long time, electric vehicles, at least those sold in the US, were kind of designed for more temperate climates than the Midwest, designed for California or whatever, when winters are not particularly cold. So they typically use electric resistance heating, which basically converts chemical energy to thermal energy at a conversion efficiency of about 1. But more recently, manufacturers have put in what are called heat pumps to do the space conditioning, space heating within vehicles. And so there you use some ambient heat in addition to the energy stored in the battery. We will talk about heat pumps in detail in 3 lectures or something like that. But the punchline is that you can cut the amount of energy you pull out of the battery for heating the cabin by a factor of 2 or 3, something like that. So that's one reason we need air conditioning or heating, and that takes more energy from the battery. The other reason, and actually, I'll just say one more thing here. So this is one area for heating where combustion engines, internal combustion engines, actually have an advantage over electric vehicles. Because if you think about an engine block say a gasoline engine, it might only be converting the chemical energy in the fuel to work to push the vehicle around at an efficiency of about 25, maybe 30%, something like that. So the remaining 70-75% of that energy just becomes thermal losses. So that's why the engine block of a vehicle gets super hot. So if you need heating, you can imagine just using a heat exchanger to absorb some of that waste heat, move it into the cabin and keep people warm. Okay, so that's one kind, cabin heating and cooling. And then the other is for battery thermal energy, thermal management. So the idea here is that batteries are designed basically to operate kind of in roughly room temperature conditions. And we talked about how, one way to accelerate degradation of your laptop battery is to do what I do and carry it around outside in super cold days, or to use it on super hot days, or to run video games while watching Netflix and just get a bunch of heat inside of your laptop. So for that reason, EV batteries typically have thermal management systems that can actually heat or cool the battery, keep it kind of within its safe temperature range, so that it doesn't degrade too quickly. But that thermal management for the battery also takes energy. Okay, but all that being said, a typical value for an energy intensity for an EV is kind of in the range of 0.15 to 0.4 kilowatt hours per kilometer driven. So 0.15 here would be like a super efficient, fairly small, fairly lightweight vehicle. And then 0.4 or even above that would be like a big truck or sport utility vehicle, something like that. Oh yeah, and just as a point of comparison, an electric bike typically uses a factor of, I think this is 30 to 80 less energy per distance driven than a vehicle, electric vehicle. And the reason for that is just, it's so much lighter, basically. Also, electric bikes also have oftentimes pedal assist. So like if you're riding a bike, provide some of the work to push it around in addition to what's being discharged from the battery. Okay, so here is just a graph of a model from a research paper now about 10 years old that studied one vehicle type. I think it was the Nissan Leaf. So this is shouldn't be directly generalized to, it's been a decade and there are lots of other vehicles on the market now. But this is what the Leaf looked like. So its design point is about 20 Celsius, roughly ambient temperature, typical temperature. And it's about 0.17, something like that, 0.16 maybe. Under those kind of ideal conditions. But due to battery thermal management and cabin heating and cooling, if it's extremely hot or extremely cold, it might use double the energy to drive a given distance. So this curve, this kind of U-shaped curve, it roughly is sort of representative of the general trend for other vehicles. For a big, heavy vehicle, the Leaf is a fairly small, fairly efficient vehicle. For a big, heavy, Tesla F-150 or something like that, you would shift the whole curve vertically upward, where the bottom of the curve, rather than being at 0.16, might be at like 0.4 or 0.35, something like that. Questions about this? Yes?
So like, sometimes people change out their tires and they go with like summer tires or spring tires. Could you design like a winter battery that has a lower?
I'm just thinking that, or like a block in the battery housing with like thermal insulation, something like that.
That is an interesting idea. I had not thought about that. And I don't know if anybody is currently doing this, but just for folks online, the suggestion is in the same way that we typically, some people in climates like Indiana, for example, where we have a lot of snow and slush and stuff like that, they might swap out summer tires and put on winter tires. Could you imagine doing something similar with the battery, where you have sort of a summer battery and a winter battery, or maybe the housing that the battery lives in? You could imagine. Yeah, move it closer to the drivetrain to absorb more waste heat coming off of that, or put in more insulation or something like this, right? I don't know if anybody really does that with full-on battery swaps, but it is an interesting idea for sure.
Yes, insulated battery housings for EVs exist and are being found in manufacturers for.
Fair enough. So manufacturers in cold climates will, yes, insulate the battery. Is there a swapping thing though? Like, do you take out the battery insulation during Okay, live Googling here.
I know that there are e-bike stations where you like show up and you trade out your battery.
Yeah,
And so, but like cars are a little bit like back when, I think I remember that from like 10 years ago. It's like, oh, this is our new car design. You can just drop it, just like an oil change.
yeah, totally. I think there was a company called Better Place. It was a startup company in like 2010 era, something like that, that got a whole bunch of press kind of in the early clean tech era. And they failed spectacularly after investing like billions of dollars in this. But the idea was basically, yeah, that rather than stopping at a fast charging station and refilling your battery on a road trip, you just pull into a battery swap station, they give you a fully charged one, and off you go. It's a nice idea. I don't exactly know why that model seemed to lose out to the sort of just building charging stations. Because something about China, what was that? They still do it in China, okay. Okay.
Swap out that, but that's like, I would need to cut that too. They're saying because the battery is it's such a large these days, the capacity, and because the housing is often integrated in the frame.
Right.
It'd be too much of a hassle.
Okay, so because the batteries are so big and because the housing is so well integrated into the frame, it just doesn't really make sense. Sorry, I'm just repeating you so that because people online can't hear what is said in the room. So, but yeah, that's a really interesting point. Yeah, the batteries are huge now. So, sorry, side note here, but my research group is in conversations with GM about getting a temporary loan of a Silverado, which can actually do bidirectional charging, meaning you can power your house off of your vehicle. I'm very excited about the research stuff that we can do with that, but it has an insanely large battery, a 200 kilowatt hour battery. So a Tesla Powerwall I just mentioned has a 13.5 kilowatt hour battery. So there's like 15 Tesla Powerwalls. And so if you look at the design of that thing, like basically the whole floor of the truck is just batteries, right? So yeah, to your point, like swapping all of that out as deeply like structurally integrated into the vehicle, that would be a challenge, I guess. But maybe for hybrids. Hey, I don't know. It sounds like maybe there's some interest in this. Maybe this is a semester project idea. You guys could kind of sketch it out. I don't know. Okay, so corresponding to this curve here for the temperature dependence of the driving energy intensity, there is a model, and it comes from that same paper. I think this was a group at Carnegie Mellon. Anyway, they give the coefficients here in the model. It's a fifth order polynomial model in temperature. If you want to use this for some purposes, remember to convert temperature to degrees Fahrenheit rather than Celsius. But the units of the output here are kilowatt hour per kilometer. So this is a weird mix of English and metric units. Okay, and then for EVs, just like for stationary vehicles, we have constraints on the charging and the discharging powers. When an EV is unplugged, can't charge typically unless you have some kind of cool wireless charging. By the way, at Purdue, there's a big project that is about basically on-road wireless charging of vehicles. So the idea is to put some power electronics, something like that, underneath the surface of the road, or at a stoplight or something like that. And then while your vehicle is sort of in electrical coupling with that, then you're charging the battery. Big idea. We'll see how it works. Some eye rolls and head shakes in the room. Okay, there's some skeptics. Yeah, right. Yeah, and then pretty much functionally, there's essentially no discharging power limit. And I think that I have one of the quick calculation problems on this week's homework is about this. So if you go, a Tesla, whatever Model 3 or something can go 0 to 60 in like 1.9 seconds. So if you just calculate like what the rate of power conversion is for that, you get some really high number. So it's around 400 kW, which if you look at how much energy a semi uses as it's barreling down the road at like 70 miles an hour, it ends up being around the same, 400 kW, something like that. Okay, but when EVs are plugged in, typically for almost all EVs that are on the market today, they can't do the bidirectional charging thing that I mentioned. So they can only draw energy from the grid. They cannot push energy back to the home or to the grid. But a limited number of EVs that are out there today can do that. And there's what's called V2X, so vehicle to stuff. And the X could be the power grid, that's V2G. The X could be a building, V2B, it could be a home, V2H. There's also V2L, or load is the L. So the idea there is that For example, the F-150 has like outlets in it, the F-150 Lightning, the electric version. So if you go to a work site, say you're a construction worker and you have a bunch of power tools, you can charge the power tools from your vehicle at the site, basically.
The Cybertruck has like crazy V2L load.
Cybertruck also has V2L capabilities, crazy. Yeah, I believe it. Yeah, okay, so how do we model this mathematically? There's kind of this dichotomy between the charging and discharging, depending on whether you're on the road or plugged in. So one way to help with that is to define what's an indicator variable. So indicator here just means that it's either 0 or 1. It indicates whether something is happening. So it's 1 if the EV is plugged in, and 0 if it's not plugged in, it's out on the road. Or maybe it's parked, but just unplugged. Then the charging constraint. So if we are plugged in, the charging and discharging constraint is looks basically like it does for a stationary battery. And if we don't have bidirectional charging, then this thing, the discharging power limit is just 0. So then this equation would say you can't discharge, you can charge, only charge, and you can only charge up to a limit PC. And then if you were on the road, basically there is no charging. So P must be negative. We can only take energy out of the battery. And then there could be a negative, like a lower limit on this, but functionally, you might as well just ignore that. So, but you could set it to something high, like 400 kW. Yes.
For that bottom one, do you have to think about things like regenerative braking, where like you could charge the battery with, gravity or,
Yeah, it's a good point. So, so the suggestion is, what about regenerative braking? So that technically is a way that you can increase the energy stored in a battery. So I guess if you lived at the top of a mountain and you just unplugged your vehicle and just started letting it coast, and then you did regenerative braking as you coasted down, your battery would end up with more energy in it than you began, converting all that gravitational potential energy. Yeah, that's kind of an edge case, and it's not modeled here, but I guess we could figure out how you could model it. Yeah, but good point. I think the main way that regenerative braking would show up in an EV model is basically through this energy intensity. So it would reduce the energy intensity kind of on average, if that makes sense. Okay, so just like in the stationary case, we can talk about how to come up with numbers for all these variables that show up in the model parameters. So we have the time constant and the efficiencies. These are typically quite similar to stationary lithium-ion batteries. The energy capacity, so this will depend on what kind of vehicle you're looking at. A small hybrid, for example, might have only maybe a 5 or 10 kilowatt hour battery. And then at the really high end, the big trucks that you see in US markets might have 200 kilowatt hours or something like that. And then there are levels of charging, level 1, level 2. So level 1 charging, people sometimes call trickle charging. And this is basically plugging into like the wall outlet that's back there or over here, which is typically 120 volt. And then the current constraint might be on the order of 15 amps. And so you multiply those and you get somewhere between 1 and 2 kilowatts typically. So, if you had a 200 kilowatt hour battery and you can only charge it 2 kW, then you need 100 hours to fill up your gigantic truck battery, which is however many days that is, I don't know, 4 days. And then level 2 charging is faster, and it's actually quite a bit faster because typically level 2 charging involves both thicker wires that have higher amp ratings, current ratings, and also typically the voltage of the circuit will be at 240 rather than 120. And so if you multiply these here, you get about 11 to 12 kW, something like that. And then, yeah, again, if you don't have bidirectional charging, you set basically the discharging limit to 0. And then if you do have bidirectional charging, typically the constraint there will be set by the wiring in the house that you're, or the outlet that you're plugging into. So typically, that wiring is basically symmetric for charging or for discharging. So you set the power limits roughly equal. So again, this is not like hard and fast rules. This is just if you want to do some quick and dirty modeling of an electric vehicle, some ways that you can kind of get to these parameters. It's also worth talking about driving patterns. Again, so like the distance d of k that I showed is an important parameter that shows up in models if you're dealing with people actually driving around. So some data on US driving patterns. Again, this is very US centric and would be quite different if you're thinking about Europe or some Asian countries and things like that. But In the US, typically households have around 2 vehicles. And this includes things like cars and pickup trucks, vans, SUVs. The typical daily mileage for driving, if you look kind of on average of the entire US, is around 26 miles, which is about 40 kilometers. And then if you look at the single trip, so the one way, you're driving to the grocery store to work or something like that, kind of the average trip in the US is about 8 miles, 13 kilometers. So if you just take the ratio of these things, you get about 3 trips per day. I imagine you drive to work, drive to the store, or drive home, something like that. Okay, and then there are distributions for when these things happen, and the numbers, I'll show them in a sec. But most trips happen basically when people are awake and not at home, so between 6 a.m. and 8 p.m. For those who have taken a class in probability or statistics, this is a probability density. For those who have not taken a class like that yet, don't worry, but also you should. But this is basically showing on the x-axis here the mileage or the kilometers that is driven on kind of the one trip, one way drive. And then the y-axis you can think of for each of these bins as basically the fraction of all trips that happen kind of within that bin. So this would be roughly the percentage of trips that happen, in a, say, 3-kilometer bin, something like that. And so this basically shows that a lot of driving is short trips, but there are heavy tails in this distribution, which means that you can still find trips that are very long, for road trips and things like that. But if you wanted to simulate driving, you could pick times when these trips are going to happen, and then you could use sort of probabilistic information about this distribution in order to generate a random number that kind of corresponds to this distribution here. So you generate a lot of numbers that are kind of down here where there's a lot of data, but once in a while you would generate a number that's kind of out here where there's not so much data. So you'd get a lot of short trips, but occasionally a long trip. Yes?
Is this distribution very much like depending on that time of day, whether it be 6 a.m. or 8 p.m., or is it same most throughout the day?
Yeah, so the question is, does this vary based on time of day or maybe other things? And the answer is yes. So this is kind of like averaged over time and space across the entire US. Certainly this is going to be different temporally. So if you look at the trip distance at 4 in the morning, it's going to have a spike at 0 because not many people are driving at that time. It's also going to vary spatially. So if you look in a big city, typically trips will be much shorter than they would be if you live kind of out in the country. Yeah, so if you want to get more specific, you would adjust basically this distribution, I think. And then here is a distribution again. This is drawn from the US Department of Transportation. It has what they call the National Household Travel Survey. So you can see there are a few trips kind of late at night and a very early morning, but the bulk of trips happen kind of between 6 a.m. and 8 p.m. And if you squint at this thing, it's kind of flat-ish. There are some peaks here kind of during, commute to work and commute home from work and things like that. But a reasonable way to kind of randomly generate trips would just be to pull uniformly, say it starts at sometime randomly between 6 and 8. Questions about this? Okay. So now I guess I'm going to do the thing that I did with last week's homework, which is to basically show you what the outputs of your code should look like in the assignment that's due next week, Wednesday. I don't think I'll have time to pull up the actual code, but maybe I can set aside a little time on Thursday to do that and walk you through, again, as people suggested, kind of how that code works. Okay, but here we're just going to talk about some simple policies for how electric vehicles are charged. So probably the simplest one that you can think of is just kind of like how like a dumb laptop charger or phone charger would work. Basically, anytime you are plugged in, you just charge at the maximum capacity and you stop once the battery is full. So mathematically, what that looks like. So first of all, we have our indicator Z, which is whether the thing is plugged in or not. So if we are plugged in, then we set the power to this thing, which is the smaller of 2 options. So again, the min function, I showed the max function last time. The min function is a function of 2 variables. Min of x and y just gives you the smaller of x and y. So if x is 12 and y is 3, it gives you 3. Okay, so here the first argument is the charging efficiency. So this is the chemical charging power. So it's just the conversion efficiency times the maximum electrical charging power, Vmax. So if this is 5 kW and this is, about 1, this thing is about 5 kW. And then this is a weird term that shows up over here. So does anyone have a guess at like what this term means? Where it comes from? Yes.
Just solve that.
It is solved out for the original equation under particular kind of circumstances, I guess. At the full charge, exactly. So this X max here basically says full charge. And then, yeah, the equation here basically says the new X is equal to the old X plus this stuff times the chemical charging power. So if you solve that equation for P chem, when substituting in X max at xk plus 1, then you get this thing here. So we're showing that here. So the dynamic equation basically is X new is AX plus 1 minus A times tau times P chem. So if we take this thing here and plug it in for P chem in that equation, this stuff cancels the denominator. We have a negative AX here and an AX over here, so those cancel. And we are left with just the X max. So this here, the thing that shows up in the second argument is precisely the chemical power that places the next energy exactly at the full capacity of that. Okay, so that's where this is where the until full comes in here. Okay, and then the second policy here basically says whether you're plugged in or not, only charge if you're below kind of a certain minimum value. So you might say 40% charge, 30% charge, something like that. If we're above that, don't worry about it, don't charge. So here we define a minimum acceptable energy, X min. So the underline means low or below. And then we need to indicate, define another indicator variable Y, which basically is, again, either 0 or 1. And if it's 1, it means we are in sort of charging mode. And if it's 0, it means we are not in charging mode. Okay, so we, at time k, we would say, okay, begin this sort of an algorithm that I'm going to lay out here. You would start the algorithm with whatever you were at in the previous time step. So you'd say, if in the last hour I was charging, I was in charging mode, then this hour I'm also in charging mode. And then this line says if z is 0. So this says if you are not plugged in, or if X is equal to X max, meaning the battery is totally full, then you change, you set Y is equal to 0. So this basically says either you're unplugged or the battery's full, so you're no longer in charging mode. And then if Z is 1, meaning the battery is plugged in, and you are below the level X min, so this basically says you're plugged in and you're below the minimum acceptable level. So the decision there should be go to charging mode, begin charging. So we set Y is equal to 1. And then after all this stuff is 1, we say, or has executed in the code, you would say, okay, if we are in charging mode, if Y is equal to 1, then we want to set the chemical charging power equal to, and then all this stuff on the right-hand side is just exactly what showed up in the first policy. So you either charge full blast, or if the battery is full, you put in just enough to kind of top it off. Okay, so the policies here are getting kind of progressively more complicated. So the first one is super dumb, just charge full blast whenever you're plugged in. The second one says only charge if you're below a minimum acceptable level. And the third one says, again, it's like the second one. So when you drop below that minimum acceptable level, you begin to charge, but rather than charging full blast, you charge at a constant power level so that you deliver kind of a full battery at a deadline that the user specifies. So I might say, dear electric vehicle charging software, I would like a full battery by 6 a.m. tomorrow in case I need to get up early and go to work. And so this algorithm would say, okay, cool, you're currently at 20%. Say we have 10 hours to charge and you want to get to 100%. So you take the whatever 80% that we need to put in, divide it by the 10 hours, and you get the rate of charging the battery so that you charge kind of smoothly and evenly over the whole night. Yes.
This is a constraint, right? I mean, from the capabilities of the charger. If you want in 1 hour of full charge, maybe you don't have the capability.
Yeah.
So this should be like, you should initialize some constraints from that, or?
Right. So the question is, or the comment is that there are constraints to how quickly a battery can charge. So for example, if you pull up your car charging app and you say, yeah, I'm at 20% battery. I want to be at 100% in 10 minutes, right? And you're plugged in at home, not a super fast charging station, something like that. Then that software should have built in some guardrails, right? That would say, you've asked me to do something that is impossible. And it would say, sorry, the best we can do is 4 hours from now, I can give you a full battery. Or alternatively, if you have 10 minutes to charge, the best I can give you is an additional 10% energy, something like that. So yeah, and I think that the way that I've written this out includes that, but I may be wrong. Sorry, was there another question or comment from the room? Okay. Right, so this is conceptually simple, but mathematically it gets a little bit more complicated. Okay, so suppose that X star, this is the amount of energy that we want, 80% charge or 90% charge. And then K star is our deadline, so 10 minutes or 10 hours from now. Okay, so the idea here is that we're going to charge at constant power P naught for the entire duration between the current time, K, so this could be time step 0, call it, and the final time step, K star. So we have our dynamic equation. This tells us what the new X at time K plus 1 will be as a function of the starting X of K, and then this charge power here, P naught. And we're going to write down a bunch of equations and eventually solve for this thing, P naught. Okay, so we can write our X2 equation here, but then X2 is a function of X1, so we can take this equation that we have on the right-hand side for X1 and plug it in here, and then do a little bit of algebra, rearrange some terms, and we get an a squared times the initial X, plus this kind of chain of products here over times tau times the charging power. And then we can iterate that forward, go to time 3, time 4, and so on, all the way until we get to our final time. And this expression basically forms a pattern here. And so we get this equation. And you can go through and kind of convince yourself that this equation is right, or you can just take my word for it. I went through carefully in deriving it. So then the algorithm basically just becomes, it's the same as number 2, but it says basically if we are in charging mode, then we charge either at oh, I see. Yeah, so here is where the constraint comes in. So this says you do the smaller of the maximum amount that you're allowed to charge. So this is your charging capacity. Or this amount here that basically allows you to exactly place the energy at the user specified value at the end of the period. So this comes, the second term here just comes from solving this whole thing for P naught chem. If you take this equation, solve for P, that's exactly this. So right here, this would basically take into account the charging constraints that you rightly mentioned. Okay, so the end here, I give a numerical example and then show how each of these 3 policies looks in a simulation, and those should be the outputs of your homework. We are at time, so I'm going to stop and we can start there on class on Thursday. If you have any final questions, feel free to hang out, but obviously you should take off if you want.